Okay, so we had a couple of theorems left that we needed to do or talk about. Theorem 2.2 for sure, and then theorem 2.7 we were going to talk about. And then I've got some more like worksheet fun. Oh, hey, wow. Welcome to all of us. You're having a secret meeting out in the hallway or something? And you're taking your quiz up the top. So I did post, I was starting to think ahead about exam 2, and I did post exam 2, just all the definitions and theorems that you need to know for the exam. And I was thinking ahead about, oh, whoops, is it going? Okay, I don't ever know what this live stream thing is doing, so. So yeah, so I did post, it basically is just a document that has all of the theorems and all of the definitions that you need to know for exam 2. There are a lot. We've actually done quite a bit in the last few weeks. So, and I was wrong before I said that it was going, starting at chapter 2. It's actually starting at section 1.3, because that wasn't on the last exam. So the prime number stuff, we hadn't been tested over yet. So the prime number stuff will be on this exam too. So it'll be section 1.3, chapter 2, the appendix on induction, and the appendix on equivalence relations. So that's what the exam will be over. Okay. So yeah, and as far as like memorizing proofs, I was kind of going through the proofs, and there are a couple I think that are like reasonable to memorize that are not, but there's not one that's like super long, like the division algorithm one. So I think what I'm going to do, I'm going to talk to Dr. Ortman today, and I think we'll pick out maybe 2 or 3 of them that's like know the proofs of these theorems, and they could show up. So I'm not going to guarantee like which one is going to show up, but like here are some proofs you ought to know, and one of those is going to be on the test. So that's kind of what I'm thinking right now. So we'll finalize that and talk about it today, and then I'll let you all know on Friday. Okay. So any questions about anything else that's coming up? How was the homework last night? It was a lot, I know, but I mean, it was a lot of problems, but I think they weren't all, some of them were computational, so it wasn't so bad. So y'all feeling okay? Okay. If you're not, please talk to me. Let me know. I would be happy to meet with you, talk about anything that you're wondering about. So yeah, so please reach out if you're not feeling, because I mean, you should feel maybe a little bit uneasy. I think that this course maybe makes you feel that way a little bit. So that's totally normal. But if you're feeling beyond that, like if you're starting to despair or something, please come talk to me. Don't just like drop this class or something crazy, because I think all of you can do this. I mean, every single one of you can do this. So it just may take a little bit of more conversations if you're feeling if you're not feeling good about it. Okay. All right, so let's do some math here. I've got 2 more theorems we need to iron out, and then we can play a little bit. Okay. So let's do theorem 2.2. So theorem 2.2, I just forgot to do last time. I just skipped over it by accident. So sorry about that. But basically what we're doing is we're trying to talk about like, what does addition and multiplication mean with these congruence classes? Okay. And so we're trying to be careful about that. And theorem 2.2 is one of the things that's going to help us say something. So here is the theorem. Okay, so it says if A is congruent to B mod n and C is congruent to D mod n, then we have 2 things. The first one is A plus C is congruent to B plus D mod n. And the second one is that AC is congruent to BD mod n. Okay. And again, like I said, this is something we've been using. We haven't really proved it. Is the green show up good enough for you all to see? Okay. Okay, so let's prove this. Okay, so how do we show that AC is congruent to BD mod N? Well, to show that, I would need to use the definition of what it means to be congruent mod N, right? So I need to show what? Well, what's the definition of being congruent mod N? So we have that, I'll use different letters. So let's say X is congruent to Y mod N. If and only if, what is it?
Difference is a multiple of n.
The difference is a multiple of N, yeah. So X minus Y equals NK for some K and Z. I think sometimes I'm saying Y minus X and sometimes I'm saying X minus Y, but anyway, you could define it either way. I think, let me be careful. Let me be careful here and see how it's defined in the book. Okay, the book does it X minus Y. So we'll try to, I'll try to stick with that. Okay, so if X minus Y is equal to NK for some K and Z. Okay, so if I want to prove this, what do I want to show? Well, I need to show that B plus D minus A plus C is equal to N times something, right? So I want to look at B plus D. Oh, gosh dang it, I did it backwards. I got it stuck backwards in my head now. Okay, so we want to say that A plus C minus B plus D is equal to N times some constant, okay? Some integer, okay. So what are we going to do? We're going to assume that what we have okay, then unpacking those definitions, what do we have? Well, we have A minus B equals NK and C minus D equals NJ for some K, J, and Z. Agreed? Okay. So then A plus C minus B plus D is going to equal what? Well, let's just distribute that negative and rearrange a little bit. Okay. So we're going to have A plus C minus B minus D. How do I want to arrange that? Well, I know something about A minus B, right? And I know something about C minus D. So if I can arrange it so I have things that look like that, then I'll be in business, right? So let's move the B here next to the A and move the C over, right? That sounds good. So we have A minus B plus C minus D equals, and we can even put parentheses for emphasis. Right now we're just really emphasizing that we have these things added together. Well, we know that that is equal to NK and that is equal to NJ. So that's equal to N times K plus J. Right. That's A plus C is congruent to B plus D. Got it. Questions on that? Does that seem good, Julie?
I'm sorry, it's not a question on this particular problem, but I know you mentioned it in the last class, but can you clarify on when it's equivalence and when it's congruence?
Yeah.
I think I confused myself in LaTeX because LaTeX has a completely different symbol for congruence.
Right, yeah. So this is actual equality, right? So this is it, just this is an equality in regular integers, right? And so yeah, and so I think that part of it is that we haven't been careful about putting the brackets around when we're talking about congruence classes, right? And so these are actual real integers, and these are real integers, but we're in mod n here. So I haven't said anything about congruence classes yet in this.
Well, I mean, like the triple equal, like is sometimes used for equivalence and sometimes. Okay, well, I guess the LaTeX command just confuses me because it's dash equiv.
Oh, okay, yeah. Yeah, so that's dash, that says this symbol is dash equib. Yeah, and it's really only used for this, we're only using it for like modular arithmetic.
Okay, and then like the.
And then this thing is dash sim for
Yeah.
similar,
Oh, okay.
yeah.
I thought that was weird. That was what it was.
So that's what it was, yeah, yeah, for similar.
And I think what confused me is that like, if you do dash congru or something, or cong, something like that, it's like the tilde and then two.
Oh, yeah.
so
And I
that's
think
why
that
was-
one would be, that one would be like, you would use that maybe, let's see, we'll use that, you would use that in group theory, I think, and then you use it in geometry.
Okay.
So this symbol shows up more in geometry than, but I think we'll use that in group theory to say two groups are isomorphic. So we'll use that later, but, well, I don't know. So some of you might take are any of you taking groups and representations in the spring? Well, you can consider it because, so what we're doing here is we're gonna start out with a little bit of algebra, just getting into it, and then we'll do ring theory. So we'll do a little bit of ring theory, but we're not gonna cover group theory. So group theory, if you take groups and representations, then you'll get some group theory. And that's like the second half of this textbook is group theory. So if you're thinking about going to graduate school in mathematics, first of all, talk to me because I would love to talk to you about that. Second of all, I think having that group theory would really help you do well in your algebra classes in grad school. So you should
Dr. Martini is teaching it.
and Dr. Mancini's teaching it and she's lovely. She's my academic mom. So anyway. All right. So let's do the rest of this here. Did that answer your question? I don't know if that did or
I
not.
think it
Okay.
was just like a technical.
Yeah, and as we go, you know, if you're ever like, what sign is that? You know, we can kind of try to talk to it. So I'll try to be careful about saying what we're doing here. Okay, so let's do the next part. So we want to prove that AC minus BD is equal to N times something, right? That's where we want to go. So how do we do that? Well, we'll have AC minus BD is equal to, well, let's see. Oh, okay, this one might be trickier. So we know that A minus B equals NK and C minus D equals NJ. What happens if I multiply those together? So this is scratch work. This is just like, let's see what happens. So if I do A minus B times C minus D, maybe some of these things will show up. You think? Let's see. Okay, so I'll have AC minus AD minus BC plus BD. No, that's not what I want. Okay, I'm gonna peek at the proof. What did they do here? Did you all look at this proof yet? Oh, that's clever. Okay. So what we can do is we can say that equals AC minus BC plus BC. So we're going to add, subtract BC minus BD. Do you see it? Now what am I going to do? Why did I choose that? So this idea didn't work. There is that. Okay, so now what can I do on this first bit? Factor out the C, right? Factor out the C of here. And what can I factor out here? The B. Why did we do that? Well, now I know this guy is equal to what? NK. And this guy is equal to NJ, right? So actually, I didn't leave myself enough room here. So that equals to N times CK plus BJ. So AC is congruent to BD. So this little trick here is a nice one. So we're adding 0 in a creative way to get what we need. And what we were trying to do is trying to create things that had this A minus B and C minus D in them, right? We needed those guys to show up so we could use what we know. Okay. All right. So that's theorem 2.2. So we've done that. The next thing we need to do is theorem 2.7, which theorem 2.7 really is talking about what are the properties of addition and multiplication of these congruence classes, okay? So when I write down theorem 2.7, I'm going to use all the brackets and all the plus signs with circles around them and all of that, right? So that's what we're going to do, because that's what we're talking about a new kind of addition and a new kind of multiplication that is on these congruence classes. Okay. So in your experience with adding and multiplying and things like that, well, it's kind of like, what do you, we saw some things that worked and some things that didn't work the same as adding and multiplying. It was really multiplying that was the weird thing, right? There were some things that were weird about multiplying. What do you remember was kind of weird about multiplying? When we were solving equations, this kind of came up. Yeah, Zach?
I know for like some of the tables, some numbers didn't have some multiplicative inverse.
Some numbers didn't have a multiplicative inverse. Remember that? Yeah, so that was one thing. So not every number always has a multiplicative inverse. We're going to keep talking about that. That's something we've noticed, and we still haven't quite nailed down what's going on with that. Okay. What else?
Didn't we had one equation where it was like there wasn't a multiplicative inverse, but it was solvable one way and not the other way. I don't remember. It was like 3x.
It was 3x plus equals 7 or 7x equals 3.
Yeah. One
So-
of those two worked and one of them didn't.
Yeah, and one of them gave us no solutions at all. And then sometimes we had multiple solutions, right? Yeah. And then the other thing that was kind of funny is that we sometimes had numbers that you could multiply together, two non-zero numbers that would give you 0, right? And that doesn't happen in integers. So that's also something that's a little different, okay? So let's nail down all of the properties of addition and multiplication of congruence classes and talk about how that's the same or different from the integers, okay? All right, here we go. Theorem 2.7 is gonna look long and it's gonna look boring, but it's kind of, I mean, yeah, I don't know. I don't know how to do this any different. What I would like to do is for you all to come up with this list, but I think that might be a little too much. Anyway, we'll see. So here it is. Okay. Oh, brackets, okay. Okay, for any congruence classes A, B, C, and Z mod n. And remember what Z mod n is. Z mod n is the set of all congruence classes, 0, 1, 2, up to n minus 1. And you can think of these congruence class representatives as being the remainders upon dividing by n, right? So you can kind of sort all these numbers. These are all the classes based on what is the remainder upon dividing by n. So each of these are sets, right? And so, yeah, so usually the representative we use is the remainder, but we could use a different representative. In other words, 2 is also equivalent. So the congruence class of 2 is equal to the set of all things that look like 2 plus nk, right? So such that k is an n, c. Right, so each of those are sets of numbers. Okay, so if we have these congruence classes, then we have the first one is closure. Well, I'm gonna go ahead and call it closure. So we have if A is in Zn, and B is in Cn, then A plus B is in Cn. So actually, I'll call this closure of addition. So addition is a closed operation, this addition on these congruence classes. Okay, number 2, so addition is closed. Then this is associativity of addition. If we have A plus B plus C, that's equal to A plus B plus. So associativity of addition. Now, associativity is one of those operations or one of those properties that you may feel like, well, duh, because you may not have had very many experiences with operations that are not associative. So yeah, so I don't know, have you had experience with a property that's not associative before? Okay, let me give you one just real quick, because I think associativity is, you feel like it's so obvious that, you know, you need an example. So what if we had that M star N is equal to M to the N, right? So this operation star, M star N is M to the N, okay? So if I do M star N star P, what's that equal to? Well, that's M to the N star P, right? So this is M to the N to the P, which is M to the NP. Agree? Okay, and if I had M star N star P, what's that? Well, that's M star N to the P. Okay, and so that means that M is going to be raised to that power, right? So this is M to the N to the P. So they're not the same thing, right? So this is an example of an operation that's not associative. That's kind of a fast and simple, quick one. But anyhow, addition with congruence classes is associative. So anyway, but just a quick example of a non-associative operation. Okay, so the third thing is that we have commutativity. So we have A plus B is equal to. So addition is commutative. Number 4, we have additive identity. So we have A plus 0 equals A equals 0 plus A. So there's this additive identity, 0 is the additive identity, right? And if you add 0 to any of the elements, then that element is unchanged. Okay, now 5. This is kind of not, okay, so for each A in Zn, the equation A plus X equals 0 has a solution in Zn. So there is some other congruence class that I can add to A to make 0. And we can see that in the addition tables, right? Remember how the addition tables looked? They had zeros going like this on them. Remember that? So that diagonal of zeros is telling us where the solutions to that equation are, okay, in our table. Okay, so now let's talk about multiplication. So those are all the properties associated with addition. What about multiplication? So we're on 6. Okay. So the first thing we have is, oh yeah, so we'll do just with distributive property. Let's do that. And that is that if I have a distributive property for multiplication. Okay, so we have a dot with a circle around it. Oh no, this is associativity. Golly, okay. I don't know why they didn't put these in order, but anyway. Okay, so multiplication is associative. This is distributive. So multiplication distributes across addition in the way you think it should. Right. And we have, if we had the addition over here, it would still work. B. Okay, 8. Oh, was that 8? Hang on, what I missed? 6. Oh, whoops, I missed 6 was closure of. Okay. So they're calling this 8. That was 7. Sorry, there's so many of these. I'm starting to. I need to get my glasses on, I think. Okay, so the 6th one is closure of multiplication. So multiplication is closed. That means if we had A in Z mod N and B in Z mod N, then when you multiply them, you're still in Z mod N. We talked about closure before, right? A little bit. I think there were a couple of homework problems where you had to say, is this closed or is this not under this operation? So closure just means if you take two things, you do that operation on them, you don't go outside the set, right? So that's what this closed multiplication is closed. Now what number am I on? Oh my gosh. Okay, so I think I'm on 9 now. Okay, there are only 10, so we're good. So this is commutativity of multiplication. Okay, so multiplication is commutative. In other words, A multiplied by B is equal to B multiplied by A. And the last one is additive or multiplicative identity. Okay, so we have A. So in Z mod N, there is an element that is a multiplicative identity, and that element is 1. Okay. So I think I've got everything on there now. So and to prove all of this, what we're going to have to do is we're going to have to take these things in this congruence notation, and I'm gonna convert it over to the mod notation, right, using theorem, which theorem does that? I think it's theorem. Yeah, theorem 2.3. So theorem 2.3 lets us go back and forth between congruence classes and mod stuff. So theorem 2.3 does that. So we'll convert it back to the mod stuff, and then we're just working in integers, right? Then we'll use that definition of mod to get things and go on from there. I'm not going to prove this because it's really long and I think it's kind of tedious. Not that it's not important, but I think I'd rather do other things than prove this. But this is a proof you can look through, and I think actually some of this proof, let's see, some of this proof might be some exercises. The proofs of properties 3, 7, 8, and 9 are exercise 10 and so on. So yeah, so all of this is not super hard to prove, but it's just kind of tedious. Yeah, Colin?
So I guess the proofs of these would be kind of based on like the equivalent properties and just integers.
Yes.
Did we ever have something like this just for the integers? Like,
Yeah, so I kind of waved my hands at that. And I just said, yeah, all the things you know to be true and the integers are true, and we'll move on with our life. So yeah. So I didn't write it all out carefully for the integers. We're about to start chapter 3, and in chapter 3 we'll be talking about rings. And we'll write out the properties of rings carefully then. So the integer z happened to be a ring. And so a lot of these properties are going to hold for z. Yep. Okay. So now I have some things for you to do. We only have 20 minutes, that's so bad. All right. So here is and I don't know if Peyton is online or not. What's that? Peyton, if you're online, I put this worksheet up on Canvas. So it's called Equation Solving in Z Mod N. So hopefully you can find that. Okay, so go ahead and get with your groups. I got a couple of other equations to solve. I did go ahead and give you multiplication tables. And since I was typing this up hurriedly this morning, I didn't put brackets around everything. But all of those things inside the tables have brackets around them. So just know that. Sorry.
Yeah, that was in the homework.
Yes, oh my gosh, it's so tedious. Yes, right. So yeah, so just know that those should all have brackets around them, but I didn't do it. So anyway, but yeah, those are the multiplication tables. Yeah. No, I won't come after that. I'm gonna run to the restroom real quick. Right.
I was thinking it was the addition and multiplication. tables that you were like, yeah, that's
Yeah.
the next one. I was thinking this was addition and that was multiplication. Yeah, this.
Yeah.
Very, very.
I want to say it's like, I believe it was 4 and 5.
What's the definition of unit?
Yeah, I think number 3 you just did last night for your homework. Yeah.
Oh. I agree with that. We also said that, we also say that, like, one, always like 1 and 1, apply to 1 all the time, and then the number just below us. Oh, yeah. Yeah, but, okay. So 1 is always gonna have. Which. And then other than that, so, yeah.
Okay, were you able to solve the equation 2x = 4 in Z mod 5? What was the solution in Z mod 5? In Z6. 2 and 5. Okay, so 2 and 5. So we have multiple solutions in Z mod 6 and just 1 in Z mod 5. Okay. And then what are the elements in Z6 that have multiplicative inverses? Okay, so what do we have?
5.
Just 5 and 1. Oh, I guess, let me do this. Look at me being careful. Okay, there we go. Okay, how about elements in Z mod 5 with multiplicative inverses? Oh, let's actually write out. So 5 inverse is 5, right? It's its own inverse, and 1 inverse is 1. So we can do that to be even more. Okay, what about elements in Z mod 5? 1, 2, 3, but not 0, right? So 0 never has an inverse, does it? Because 0 times anything is 0. Okay, and so what's the inverse of what? So I know that 1 inverse is 1.
And then 4 versus 4.
4 inverse is 4.
2 versus 3. 3 versus 2.
All right, good. Good. So we've been talking a lot about elements that have multiplicative inverses, and there's a name for that, which we haven't been using yet. The name for that is a unit. So these are called units. And so let's write out the definition of a unit. So an element A in Z mod N is called a unit if the equation A times X equal 1 as a solution. So isn't this interesting, because this kind of correlates to property 5, right? So property 5 said that for any A in Z mod n, this equation with a plus sign there equal to the additive identity always has a solution, right? But that's not the case with multiplication. We don't always, so this is telling us that we have additive inverses. For every element. That's what this is saying to us, right? So every element has an additive inverse. Okay. And this unit is the elements that have a multiplicative inverse are called a unit. Okay. In other words, there is an element B such that A B equals 1. In this case, we say that A inverse. Okay. So that's what a unit, that's the definition of a unit. Okay. So we had talked about this before, we had conjectured about this before, but when do elements of Z mod n have multiplicative inverses? Did you have a chance to talk about that in your groups?
Yeah, I think we said that when n is not divisible by k.
Okay.
Multiplicative inverse.
So we could say,
We also said 1.
Well,
yeah, so. So an element A in Z mod n has a multiplicative inverse when, say it again,
n is not divisible by k, so k does not divide n.
when, oh, you're using,
I'm sorry.
that's okay, I can use me. When k does not divide n. Well, look in Z mod 6. 4 does not divide 6.
Did we say it does not divide, or did we say co-parent?
I think we talked about that.
We did talk about that as a class. Remember talking about this?
Yeah, they're relatively fine.
When they're relatively prime, right? Yeah, so we can say it this way, k and n are relatively prime, so their GCD is 1. And I think that is a theorem. And we're going to prove that this is actually theorem 2.9. And so we'll prove this later. Okay, so this conjecture is actually a theorem 2.9, which we'll prove in a little bit. Not today. But yeah, this is true. Okay. All right, so go on and you should, so we just did up to number 5. So talk with your groups about number 6 and so on. 6 and 7.
Yeah.
13.
I don't remember that.
Oh, no.
So plenty of work on it.
I was like, whatever the next one.
Yes.
I like that.
Yeah.
Oh, and my office hours tomorrow will be virtual again, unfortunately.
So is that like-
So you have a mod and there's 0 dividers, get your product. Yeah.
Okay, in ZMod 6, did you find any elements that had a product of 0 that were non-zero? What do we have in ZMod 6? So 3 times 2 is 0, right? What else? 3 times 4. Since I have commutativity, I don't have to write the other two now, like, right? So we've got commutativity now, so. Yeah, and so we have some solutions, some non-zero solutions to A times B equals 0. Okay, what about in ZMod 5? There aren't any. So if we look at the table for ZMod 5, the only place I see zeros are on that first column and first row, right? I don't see any zeros on the inside. So there are no A, B, such that A, B equals 0. No non-zero and B such that that's true, right? In ZMod 5. Okay, good. Thoughts on this? What would be, let's define a zero divisor. A zero divisor. So a non-zero element, A of ZMod n. If there exists a non-zero element C in ZMod n such that a so that's the definition of zero divisor. Okay. So we would say that 2, 3, and 4 are zero divisors of ZMod 6, right? So we could say 2, 3, 4 are zero divisors of ZMod 6. And we could say that ZMod 5 has no zero divisors. Any conjectures about zero divisors?
2, 3, and 4 are not co-prime with
2, 3, and 4 are not co-prime with 6. Mhm.
So anytime that n is prime, maybe there's not a zero divisor.
If n is prime, there wouldn't be a zero divisor because every remainder would be co-prime with that prime number. Yeah. Yeah, and so so that's why a lot of times we'll talk about in the whole next section, section 2, 3, is the structure of Z mod P, right? The structure of Z mod P is going to be different from the structure of Z mod n, where n is not prime, right? Because when n is not prime, we have these zero divisors to worry about. Okay, and so and we're going to end up with that Z mod P is actually a ring, right? So this is ends up being a ring. Oh well, you can create a ring out of Z mod P. Yeah, so it doesn't have any zero divisors. Okay, I think that's all time we've got for today. We'll do some more equation solving next time and talk about the zero product property in Z. And yeah, so we're gonna make it through. So tomorrow my office hours will be virtual from 2 to 3. If you need to meet with me another time, I'll be around online if you need to meet with me. So I'll try to check my email frequently tomorrow, but if you want to set up a meeting with me today for tomorrow, that would probably be ideal. Then I can put it on my calendar. Okay, how do I end this?